Okay. We already kind of saw degree centrality and eigenvector centrality, but in this module we'll see things in greater detail. Um, so what centrality really means? So we want centrality. We call it as metric. So that means we want to quantify. Okay, so centrality metrics, they have some value. So what they capture? So the centrality metrics are computed for the vertices in a graph. So the values of the centrality matrix quantify how important is that vertex for the graph based on its location. So based on where it is located in that graph. So it quantifies the topological importance of the vertex in a graph. Okay. So let us use this example. So if you look at this graph here, so if you consider based on the number of neighbors, then x and z have the most number of neighbors. They have 3 neighbors each. So from the number of neighbors, which is degree, so from a degree centrality point of view, we can say x and z are the most important because they have more neighbors. But just having more neighbors does not make you to be the preferred vertex for all purposes. The sense that are you kind of close to majority of the vertices? Probably not. X is closer to these two vertices, but x is not closer to these two vertices. Similarly, z is closer to these two vertices, but not closer to these two vertices. Whereas y is kind of relatively closer to all the vertices, because the maximum distance which for y to any vertex is 2. It's like a distance of 1 to x and z, and the distance of 2 to the other 4 vertices. Whereas for x, it takes a distance of 3 to these 2 vertices. You have to go to y, then to z, and then take this edge to this vertex. So for x is a distance of 3 to these 2 vertices. Similarly for z, it's a distance of 3 to these 2 vertices. So with respect to what is called closeness, okay, we can say y is relatively more closer to every other vertex compared to the other vertices out there. So we'll see later a metric called closeness centrality, and that essentially captures this. So we will come up with a score for each vertex, and the convention will follow is for any centrality metric we'll look at the scores. The larger the centrality value for that vertex based on that particular metric, the more important is that vertex for that whatever the purpose that metric captures. Like in this case, y is going to have a larger closeness centrality value, so that means it is relatively more closer to every other vertex. Now, there is another important centrality metric called Betweenness that we are going to look at in detail in this module. So Betweenness again kind of indicates by the term itself how many pairs of vertices go in between, or not in between, go through a particular vertex. So again, from Betweenness point of view, y is the most important vertex for the graph, because if any of these 3 vertices, you can say this is one community or a cluster, want to communicate with any of these three vertices in this cluster, they have to go through y. There's no other way any of these 3 vertices can communicate with any of these 3 vertices. So from that point of view, we can say, by communication we prefer shortest paths. So let's say x may want to communicate with any of these 3 vertices. So there are 3 shortest paths there, x to each of them. Similarly, this vertex to each of these 3 vertices, then this vertex to each of these 3 vertices. So all those 3 times 3, so 3 vertices times these 3 vertices, there are 9 shortest paths that you are going to have between these 2 partitions, and all of them will go through y. They will not go, there's no way for them to go through some other vertex. So from Betweenness point of view, y is the most important vertex in this graph. And also Betweenness indicates, like, if you remove that vertex, it's not intended to capture that, but it also kind of could be used to interpret from that point of view. So if you remove that vertex with the largest betweenness, the graph is more likely to get disconnected, and that's true here. If you remove y, the graph is going to get disconnected. Now, if you are wondering about the betweenness of x and z, they're not going to be that high. Of course, x facilitates communication between these two vertices here with any of these four vertices. But that's going to be 2 times 4, which is 8 shortest paths go through x. Similarly, z facilitates communication between these two vertices here with these 4 vertices. So that's going to be again 8 shortest path. Okay. No, and y had 9, and it really facilitates communication across this cluster between the two clusters. Okay, so in general, we are going to look at 3 categories of centrality metrics: the degree based, the shortest path based. Thought I saved this, so we're not going to look at this one. Thought I had an updated version. 1 second. Okay. Okay, so the degree-based centrality metrics, shortest path centrality metrics, and then the hybrid of these 2 categories. Now for each category we will look at 2, the first 2 will get 2 each, and then for last one we will look at 1 metric. So just from the definition point of view, we kind of saw for what the degree centrality means. So again, for centrality metrics we are going to compute for each vertex. So the degree centrality of a vertex is basically a measure of the number of neighbors of that vertex. So number of vertices adjacent to the vertex will be considered as a degree centrality. So the number, so it's not the set of vertices, it's just the number of vertices that are the neighbors of a vertex. It's called the degree centrality. Then the eigenvector centrality quantifies how important is a node based on not only its degree but as well as the degree of its neighbors. So it captures all these things together as one single metric, quantifiable. So it's a measure of the degree of the vertex as well as the degree of its neighbors. And when we look at the algorithm, we'll see the details of this definition. Again, I've showed you in the previous module what does really mean. Okay, so it's not sufficient for a vertex by itself to have a larger degree. Its neighbors should also have a larger degree for that vertex to have a larger eigenvector centrality. Now, the shortest path based metrics, so we are going to look at the betweenness centrality as we just saw this case. So it's a measure of the number of shortest paths a node is part of. Okay. So how many shortest paths, or really what fraction of the shortest paths between any two vertices go through that particular vertex. So that is betweenness centrality. Now the closeness centrality is a measure of how close is a vertex to the rest of the vertices. So we are going to find the shortest paths from the vertex to every other vertex and find sum of the shortest path distances, and we'll do that for each vertex, and whichever vertex gets the largest sum of the shortest path distances is considered to be relatively more closer to the other vertices. Now the hybrid centrality metric. So the degree centrality metric just takes into consideration the degree, okay, of the vertices. Whereas the shortest path based metrics takes into consideration the shortest paths as well as the closeness of a vertex with everything else. So this hybrid centrality metric here, the local clustering coefficient based degree centrality, brings the best of both categories, short degree and shortest path based metrics, and tries to quantify the topological importance of the node based on both degree and shortest path. Okay. And later we'll see that this local clustering coefficient based degree centrality is kind of equivalent to betweenness centrality, and also this hybrid centrality metric is computationally efficient than betweenness. So betweenness takes a lot of time to compute, and we'll see the reason for that as we go through the algorithm for betweenness centrality. So that was introduction to cover all the centrality metrics, and now we'll look at the details. So let me save this video.